Hello and welcome to our fourth year design project symposium presentation. My name is Wesley Walker and this is my partner Millie Wang, and we will be presenting on behalf of Group 14. And today we'll be telling you about our fillable microneedle patches. As a quick little overview of the presentation, we'll first be going over the motivation behind our project, the problem we're trying to solve, what our design is, how we tested it, what our prototype is, and the main challenges and takeaways from our project, as well as the next steps. So the global drug and gene delivery market is quite large, being valued at roughly $379 billion in 2015. When you think about pharmaceuticals, people tend to first imagine injectables, just simply because injection is a very useful drug administration modality, as it allows for really rapid and efficient drug action with nearly 100% bioavailability almost instantaneously. However, it's very invasive and typically requires the use of, or the help of a trained medical practitioner, such as a nurse, for administration. On the other hand, transdermal drug delivery is incredibly user-friendly and effectively painless. However, it suffers from long onset times and a really narrow scope, as only certain small molecules with certain partition coefficients are actually able to diffuse through the skin, so you can't use it for all drugs. And what we want to do is develop an intermediate drug delivery device that combines the benefits of both platforms while minimizing the weaknesses. And a very good way to do this is with the help of microneedles. These tiny little needles are on the order of microns, and what they do is they puncture the stratum corneum, which is the layer of skin that provides the largest barrier to diffusion. And in doing so, you can create these pathways that allow drug molecules to diffuse through the skin much more quickly than they otherwise would in intact skin. These microneedles can be solid, hollow, coated, or dissolving, but in all cases, the end result is to achieve faster and more efficient drug delivery. So given that we want to effectively have an all-in-one solution that combines the use case of the hypodermic needle and the transdermal patch, all of our design requirements come from these platforms. So, for example, we need to achieve quick and efficient drug delivery, much like an injectable pharmaceutical. We'd also need to achieve mechanical stability so that microneedles are not being embedded in the patient's skin and causing an inflammatory reaction. We'd like to minimize pain. We also would like to achieve variable dose capacity to allow for personalized medication. We need the design to be durable and leak-proof, as we'll be working with liquid drug solutions. It needs to adhere to the skin, much like a regular transdermal patch, and it needs to be very easy to use. And this brings us to our proposed design, which is that of a fillable microneedle patch. This microneedle patch incorporates these two-dimensional punch-out stainless steel microneedle arrays, which were generously provided to us by our industry partner, Ex Vivo. And these microneedles will be the ones that are puncturing the stratum corneum and allowing for faster drug diffusion. This array is incorporated with an elastomer backing layer, which will expand to accept variable drugs volumes. And then drug delivery to the patch is accomplished using a tubing and septum. So on the market, this patch would come unfilled. You would be able to buy it off the shelf, and it would be up to the patient to load it with their prescribed dose. So this is really useful for anybody that needs a certain dosage. And this is in contrast to typical transdermal patches, such as nicotine patches, which come with a prescribed dose of, for example, 10 milligrams, whereas you would be able to adjust this based on your prescription.
So given that we had these microneedle arrays from Ex Vivo, we had two particular types. These are some SEM pictures of what they look like close up. So on the left, you have what we call our no window array, which you have a solid microneedle. And the windowed array, there are cutouts through the middle of the needle. And these were originally designed based on the fact that they would perhaps help diffusion because there's like a small reservoir area. So one of our most important things first to test was for mechanical durability. We don't want these needles to break off into the skin and remain embedded. That's a health hazard. So we used our test membrane, and we embedded these microneedle arrays in the test membrane, conducted our usual testing that I'll discuss in a bit, and then removed these microneedles and inspected them. So we wanted to see maybe how many had been flattened, if any had been broken off. For the no window array, we found that 45% of the needles have been flattened, and for the windowed array, 52%. We do want to note that although they were flattened, this doesn't mean that they weren't able to puncture the test membranes successfully. There were still holes consistently made in the test membrane. The flattening we attribute maybe due to the structure, how we remove them, but it was consistently puncturing the test membrane itself. So from this, we determined that although they were pretty similar, perhaps the no window array was slightly more stable. So this kind of led us to do our diffusion testing on the arrays themselves. So our most important component of our project was to quantify the amount of diffused drug through the microneedle array through the test membrane. And we did this by first building these small-scale diffusion testing cells. So they were made out of centrifuge tubes and syringes. This acted as the reservoir from which we could load more clear water, collect samples throughout time intervals. We decided to use Strat-M as our test membrane, which is a well-known synthetic skin analog. The structure of Strat-M itself has two layers. The top layer, which would kind of simulate the top layer of your skin, is very hydrophobic, it's very slippery. If we were to put water on it, it would kind of just slide off. The bottom layer of Strat-M is a lot more porous and passive to diffusion. We also decided to use methylene blue as our test molecule, as methylene blue, from what we've tested, doesn't diffuse through the test membrane without the help of a microneedle array. We've left it for hours on end and no diffusion was observed. It's also dyed so that we're able to quantify our results afterwards using UV vis. In testing these microneedle arrays, we collected samples over a period of 1 hour throughout. This is mainly due to the fact that we don't want our product to be something like a transdermal patch where you have to leave on for 5 hours, 6 hours. We want that onset to be within the hour time period. So from our testing, we found that between the two microneedle arrays, their membrane permeability was pretty similar. The concentration of the drug or the test molecule that makes it through that microneedle array into the main chamber of the diffusion cell is increasing over a period of time. The windowed array, which has that cutout in the needle, was found to be slightly better, but at the same time, we had a lot of issues with variability of data in that case. Sometimes we got a lot of diffusion at once, sometimes we got very little than expected. So due to these initial diffusion testing plus our mechanical testing, we concluded that the arrays with no windows, which is the entirely solid microneedle, would probably be our best bet in order to get a mechanically stable patch that doesn't have any breakage, as well as less variability so that we can achieve higher consistency in our results. So using this array with no window, we built our first series of prototypes. So this on the left is the top view. This is built pretty similarly to what Wes showed you before with our design prototype, which is an elastic nitrile backing layer attached to our microneedle array. And on the side is tubing and a septum so that we can load the patch with our syringe.
Okay, so in building and designing and testing our prototype, we came across a few key design challenges. The first of which is due to the large size of the tubing used, as you can see here, we have a lot of wrinkling in the elastomer backing, as well as some tenting occurring near the septum. This is not ideal, as when you load the drug, this creates essentially dead volume that the solution is able to hide away in, as opposed to being forced into the array and onto the surface of the skin. So it's really important to minimize this dead volume in order to get accurate amounts of drug to the patient and not have them systematically underdose. So the solution to this is really simple. It simply involves using smaller components for the tubing and the septum, as doing so will reduce the effect of this tenting. Also, we were able to improve it as we made more and more patches simply by making the elastomer membrane kind of conformed to the tubing as opposed to simply stretching it over top of everything. And that helped with reducing the dead volume. The next problem we ran into was poor adhesion between the microneedle patch, the actual stainless steel array, and our test membrane. So while the patch itself was perfectly sealed and did not leak, we had a lot of problems with leaking at that array test membrane interface because, as you can see in our photo here, actually the vast majority of the bottom of our patch is open. So if there's any leak or any poor adhesion in any of the corners, our liquid solution will just run off the surface of the test membrane or the patient's skin. So the solution to this is to use a waterproof medical grade adhesive, which we didn't have for our testing, but a good example would be, for example, an acrylate polymer or any pressure sensitive adhesive. In the meantime, what we did is we obtained a new diffusion cell which used clamping to hold the stainless steel array to the membrane, which effectively eliminated all of the leaking problems and allowed us to continue with our validation tests, as we didn't want to have to wait for this new adhesive. However, even though we were able to effectively eliminate leakage entirely, the diffusion in our entire patch was significantly lower than expected. Given that the patch is 16 times larger in area than our small-scale diffusion, we expected diffusion to be very rapid with this patch, but we found that this actually was not the case, with most of it simply not diffusing at all. And this caused us to question the validity of our initial diffusion cell, and through a little bit of testing and troubleshooting, what we found, and our current working theory, is that the old diffusion cell, the way it worked is we had to apply the membrane over the top and then screw on a lid to clamp it. And in doing so, we believe that the membrane was being stretched out. So when you puncture the membrane with the needles, the membrane is somewhat elastic and will conform to the needles. But once you start to stretch the membrane, these holes are being essentially pulled open, significantly increasing the pore size and allowing for drug to diffuse through the membrane at a much more rapid rate than what it should be. So essentially, our previous diffusion data has a systematic error that caused the diffusion to be overestimated in all cases. The solution to this is actually interesting, and well, essentially, this problem signifies that passive diffusion is not sufficient as opposed to our initial results because it simply will not go through the holes. But what you can do is if you apply or build up pressure at the membrane interface, these holes can be effectively forced open and allow the test molecule or drug to force itself through the holes of the membrane. And this pressure can be generated passively simply by loading the patch, which causes the elastomer to stretch, and it will attempt to restore its initial shape, which will apply a force to the liquid and force it through the patch. Alternatively, the pressure can be applied actively by the end user by simply pushing on the patch like this and forcing all of the drug molecule into the patient. This is demonstrated here with our pressure-driven flow experiment. What you're seeing is the underside of our diffusion cell, and we injected methylene blue into the patch at time equals 0. There's a little bit of methylene blue that made it through within the first 40 seconds due to accidental pressure application of the test patch. However, we started to apply pressure after 40 seconds, and you can start to see these blue dots form the second that we start to apply pressure. And over the next second, as we apply more and more pressure, you can see that the methylene blue starts to diffuse through the membrane significantly faster than it did without any pressure. As you can see, we continued to apply pressure for 30 seconds, and you can see that those final 30 seconds of applied pressure resulted in significantly more methylene blue getting through the membrane than in the first 40 seconds where it was simply passive diffusion.
So from the series of testing we did, we learned some key lessons, some key takeaways. First, mainly that these stainless steel microneedles are able to puncture the skin without significant mechanical failure in the form of breakage embedded in the skin after removal. And puncturing the skin membrane with these microneedles do significantly increase drug diffusion as opposed to just having the test molecule on top of our skin membrane and in that case where no diffusion occurs. One thing we didn't foresee was that selecting the appropriate adhesive would be so important to the proper function of our patch. And ultimately, that passive diffusion is not an adequate system to drive that dosage in the patch through our test membrane, and that pressure-driven flow is necessary if we really want to achieve those rapid onset times. From this, our next steps would be to screen adhesives for compatibility, mostly that they're waterproof and they can deal with the pressurized system that we're introducing, as well as incorporation of pressure-driven flow into the system. From our testing, you can see that we can simply do that by just having the end user apply force to the patch after application. To wrap up, we have some acknowledgments. We really want to thank Ex Vivo Labs for their guidance, provision of the microneedle arrays, our consultant, Dr. Botsui, as well as Dr. Chris Backhouse, Jen Coggin, and Neil McManus for their help and mentorship throughout this process. And we'll take any questions now.